my name is Peter, and I work for a company called RoboFlow. So we are a startup that offer computer vision services to software engineers and engineering companies. So pretty much you can train computer vision models and deploy them without knowing almost anything about computer vision. And I myself, I am involved in computer vision for like 6-7 years at this point. In the background, you see some of the projects that were probably mentioned in the introduction. For the past year or so, I become more and more heavily involved in vision language models, which brings us to the topics of today's presentation. But before I start, I'd like to do a quick hand poll. I like to do that to know who I'm talking to. So how many of you have any experience with computer vision models? That can be training, that can be calling API that hosts the computer vision model. Okay, so I don't know, 10%. Any of you have experience with vision language models? One person, two, okay, that's awesome. Some of you might actually do that, you just don't know because vision language models are maybe not necessarily the most like mainstream name for what is happening, but that's awesome. In that case, I'll have the opportunity to kind of like introduce you to the topic, which is pretty cool. Okay, so let's talk about history, and it's pretty funny to call it a history because it was like 5 to 10 years ago, but in computer vision space and in machine learning space, 5 to 10 years is it's a lot of time. We move fast. So back then, the computer vision space was pretty stagnant. We had few well-established tasks like object detection, segmentation, classification. Probably some of you remember things like that from the university. And most of the kind of like efforts in the space were related to optimizing those models. So making them smaller, making them faster, running on smaller devices with less compute power, and that's pretty much it. So it was not that interesting. However, everything changed around 2021 when a company who most of you know, from releasing ChatGPT, OpenAI. At some point, they actually released models in open source, released a CLIP model. That was a model that changed everything. So CLIP is, and I will try to keep it as high level as possible. CLIP is a model that actually contains of two elements. There is image encoder and text encoder. And how it works is when you pass an image and a text that have semantically similar meanings, like for example, here's me and my dog, and we have a sentence, a man holding a dog. Those image encoders and text encoders will produce vectors that are very similar to each other. I tried to express the similarity with color, but you get the point. It's a very long vector with like 512 items. And when you calculate cosine similarity between those vectors, it turns out they are very similar. Contrary, if you would have a text that is further away from the semantic meaning of the image, that embedding vector kind of like goes away and becomes less similar. If that would be a woman holding a cat, it would be even less similar. You get the point. So that idea changed the whole scene in computer vision because suddenly we are no longer talking only about vision, we talk about mixing language with vision, and that opens up a lot of possibilities. Just from this idea alone, you can now compare text and images for similarity, or you can use the embeddings vector to look for similar images. So let me show you two examples of that, hopefully. So here is a very simple application where what I did is I pasted like 10 names of different breeds of dog. And then I uploaded an image of my dog, and I just ran it. And it turns out from those 10 names, it's very blurry, but from those 10 names, it got the right answer, saying that it's a beagle. So that means that we calculated vectors for each of those 10 names. We calculated vector for the image, and we see that those vectors were the closest matching vector. In case of clip, which is over here, it was like 99.9% sure that it is the right brief of a dog. Now, another example of the application that you can do, or thing that you can do, some of you who are very quick thinkers probably noticed that one of the demos that I showed in the introduction was like football AI demo, where players were detected, tracked, divided into teams. A lot of things is happening there. But one of the things that is happening there is dividing into teams. And what you can do is you can crop out the players and you can calculate embeddings for them, and then use clustering algorithm. Each of those dots is actually representing a single crop with the player, and then you can see that they got accurately divided into teams. And those images are not always very simple to do. Over here we have teams with red and white, but those colors can differ and can be actually a lot harder for the person to accurately understand which team is it. So now, what happened is that Clip pretty much over the night took the whole computer vision scene upside down. This is the amount of papers, research papers about vision language models year by year. So this is the year the Clip got released. Probably some papers were still in 2021 after Clip got released. And this is where we are here. I was on CVPR, which is the biggest computer vision conference in the world this year. And I would say like 60 or 70% of papers were about mixing vision and language at this point. So if anybody would like to change your profession, and it's actually the best time to do that, because everybody who is doing that for 10 years, whatever they know is no longer valid. Pretty much all the research happened in the last 2 years. So pretty good time to do that. Okay, so first Clip, very similar, very simple application. We just compare vectors, but we are 3 years later, so what we can do now? So first of all, there are like a ton of new vision tasks. So previously, like I said, detection, segmentation, classification, those are the things. Now we have pretty much any week there is like new computer vision task, because you can come up with something to do with vision language models. But here are the kind of like the simplest. So many of you heard about the captioning of the image. That's a task for vision language model. Zero-shot detection. So for example, here is the outcome of one of the models. I hope that I will have time to show you that model live. But I ask for the tail of my dog, which is kind of obscure object. Like, it's not a person, it's not a car, it's a tail. And it managed to successfully detect that. And you can ask questions about images. So you can, for example, ask what breed of a dog is it, and it's a beagle. Very similar task to what we done with Clip, but actually executed in a completely different way. And all of those tasks open up new possibilities. And the best thing about it, each of them, even detection, even segmentation, is executed by a single model. So you can think about it, okay, previously, if I would like to execute tasks like that, I would need to deploy like 5 different models and have complicated infrastructure to do that. Right now, it's a very simple infrastructure and a little bit of prompt engineering, and that's it. So that's why a vision language models are so powerful. Here's an example of something that would require probably 3 to 4 models previously. So we have a brand of the car, the color, the license plate, and the car is detected. Previously, those would be 4 different computer vision models. Now you can run separate queries for the VLM. One asked about the brand, one asked about the color, asked to detect that and read the license plate, and it can do OCR and extract that. And VLMs are actually a lot better at OCR. So if any of you that did OCR in the past, those times where you use Tesseract or whatever library you used probably are gone, because VLMs are way better at OCR than anything before. And maybe I will show you examples if I will have the time to do that. So few demos that used VLMs. That's why I said if only 2 people raised hand about VLMs. GPT-4 Vision is also VLM. So of course, like when that model was released probably a year ago, you could build a chatbot and chat with the video and ask it about things that are happening over there. I'm doing very simple things like asking to read the hour from the phone, or ask it what MBA team is on my cap. But you know, opportunities are pretty much limitless. And what else we have here? Oh, this one is also quite interesting because you can use language to detect things. So previously, if you did object detection, what you did, you need to train the model specifically for those classes. So if I want to detect glass bottles, for example, then I need to collect the data of like hundreds or thousands glass bottles, come up with you know, creative ways to augment that data set, and then train the model, and it can detect glass bottles. But then if I would like to add plastic bottles to that equation, it will no longer be able to do that. You need to once again go through that whole process, retrain the model, spend a lot of time and money probably. So VLMs are awesome because they are capable of zero-shot detection. So you can pretty much come up with the classes on the fly. Like I had a photo taken over here in the city, and I was like, okay, I would like to detect the, I believe, white napkin. Okay, then I said, so let's detect the dark napkin, yeah, and it got detected. Then I said, I would like to detect the straw, and got detected. Then I believe the dog and my hair on my head, and it all gets detected. I combine, in here I combine the model with segment anything model. That's another model that is not VLM, but it's perfect. That model can convert bounding boxes that you saw previously into like pixel perfect masks. And there are variations of that model that can run really fast, like real time. So for example, if any of you would like to do real-time segmentation, that's pretty much possible at this point because those models got very small and fairly fast. Another example of something similar is processing videos. So you can combine zero-shot detectors based on VLMs and some to detect and track object across the video. And that's another thing that can open a ton of possibilities in applications, because you can right now use language to describe what you would like to do with the video, rather than you know, spending time you know, annotating keyframes and looking for the segmentation masks. So what I did here is I came up with like very high-level prompt where I would like to detect the player in white and black outfits, ball, and the rim. And yeah, hopefully it will play through. It did exactly this. And how it happened is that we probed a few frames from the video. We ran that query on each of them, and then we use segment anything to track across the whole video. Very easy now. So here's that. Under the hood, the vision language model are not like that different from the clip that was released in 2021. We still have image encoder, we still have text encoder, but what we do is we calculate those embeddings and combine them, concatenate them into a single vector. So we have a very long vector of embedding. Part of that vector is are tokens from images. Part of that vector are tokens from text. And then we train the decoder. The decoder part is the new part that can understand that combination and reason about those things and produce those answers. And there are like 2 ways to do things right now. So of course, OpenAI releasing ChatGPT and then GPT-4 Vision, they were like kind of like the first company that released VLMs that were good. And they have this approach of training gigantic models, models that are behind the APIs. Almost no company release those models to the public in the way that you can have your weights and deploy them. But to be honest, that wouldn't really help because you need like 32 H100 GPUs to run that model anyways. So it wouldn't help you a lot. But that was the approach that enterprise took. And open source community took another approach, which are task-specific models. So the previous models, you know, if you go to ChatGPT, upload an image, you can ask about what movie is it. You can ask about what city is it. So it has like broad understanding of the like context, social context, geographical context, you know, things like that. Task-specific models are not necessarily like this. They also have some knowledge and they can be pretty good at some tasks, but they are designed to be fine-tuned. So what you do is you add those capabilities by training that model on specific things, and then you can leverage the fact that it already has understanding like a VLM, so it can do things, and you add that specific thing that you are interested in on top of it. That's how open source community works. It is pretty cool because contrary to traditional computer vision, if you would look at those object detectors, segmentation models that are released in the public right now, most of them have very restrictive licenses. VLMs, because all the major companies try to checkmate each other into, you know, not being the leading part. Every large company, here you have Microsoft and you have Google, but you can add Meta to that. They all released VLMs in public space. They all released it on the very permissive licenses, MIT, Apache. And those, some of you probably don't really know what does it mean that the model has 3 billion parameters, but that pretty much means that you can deploy it on a regular GPU. If the model like Florence II has 0.2 billion parameters, it can be deployed on a phone. And you can get those capabilities on those devices. And like I said, all of them are very permissive, so you can build pretty much products on top of that. And yeah, I wanted to show you what you can do with those models. So this one is Florence II. To be honest, that's my favorite one. This is the smallest one. Florence II supports, out of the box, supports like 14 different tasks. I will show you some of those tasks. And that's all the time. This is the same model. I don't reload new models. I don't do anything crazy over here. I just use different format of a prompt. So to communicate with Florence II, you have this, I'm not really sure if you see that. You have this kind of like predefined way on how you name tasks that it can execute. This OD, this, yeah, it's object detection. The only one that use abbreviation, which is a little bit inconsistent, but okay. And when I run it on the image, once again, image of me and my dog, that's a common theme in all my demos, you can detect a lot of things out of the box without any training. A lot more than typical computer vision models because they are based on Cocoa and they only detect like 80 classes. Here we have more classes. We have like wheel of the car. We have like human face. We have footwear. We have all sorts of different things over here. But of course, that's not enough. Let me just run the utility cell. It offers captioning in 3 different sizes or maybe precision levels. So it's a captioning, which is pretty much like a single sentence explanation of what you see on the image. But you also have like detailed and more detailed, very nice names. So over here, if you run more detailed captioning, you will get a quite detailed explanation. A man sitting outside on a bigger chair. He's wearing a black cap, sunglasses, a blue shirt. Yeah, so it matches what is happening. And you can also do things like I did before. So like I said, you can, for example, ask for specific object. In that case, a tail of my dog, and it got detected. So you are not bound to classes that are predefined. You can actually come up with classes. Sometimes what you need to do is you cannot detect the class like directly, and you need to be more creative. So you need to come up with like few word explanation of what you are looking for. and it gets detected. And what else do we have here? You can combine the tasks, for example. So you can use captioning as an input to Florence once again. So use Florence to create caption, and then use Florence to convert caption into bounding boxes. And then we have this situation when we run a model. We get a description, hopefully at some point. And the description is, in the image, I can see a person sitting on a chair and holding a dog. And when we look at the bounding boxes, we have a person, the chair, a dog. And if you would like analyze the rest of bounding boxes that are here, those are all bounding boxes coming from the sentence. So over here, I use that as a pretty silly example, but you can imagine a situation that you can use that to extract position of objects that are on the image when, I don't know, user provides a very rough description of the product, and you extract all that information. You can locate those specific things on the image. So you can use it in all sorts of creative ways. This one is also very interesting, probably the last one that I will show. Let me just only adjust the resolution of the image so you will see more. So this one is a little bit different. It assumes that you don't have the description and just give you bounding boxes with more advanced descriptions so you can maybe use them. So I don't know, here is a blue sneaker. Previously it was called footwear. Here is a bounding box with me, but I'm holding a dog and I'm sitting on a chair outside of cafe, so I get that description to that bounding box. So there are I was wrong. That's not the last task that I want to show you. I want to show you the OCR because I was like hyping the OCR. That is really good. Yeah, mind you, that model is small enough to run probably on a phone. So here is the image of the car where I asked it to perform a task called region OCR. So there are two tasks. There is OCR and region OCR in Florence II. So with OCR, it just dumps all the text that it sees on the image. With region OCR, you get the bounding boxes and the text associated with the bounding box. So in our case, if we have license plates, we could extract that information this way. You could also, for example, detect the license plate and then read it from the bounding box, but that's a possibility as well. But this is one of my favorite examples where the text is actually quite low quality, I would say. It's a handwritten note. It's pretty hard for me to read it correctly, and probably don't see the text that got extracted, but it was 90% accurate, which for words like this, which if you would ask me what is that, I have no idea. It's pretty good. Yeah, here is the example with the typical OCR where you just dump the whole text. You can do segmentation, you can do all sorts of different things. You can point out a specific object and get descriptions for that object. So this is VLMs. You can run multiple tasks in a single model. Model is pretty small. And like I said, you can fine tune it. So for example, I still have a minute, so I will just say one of our engineers right now fine-tuned a different VLM, a little bit larger, to extract, to process research papers in the way that you extract information from the paragraphs, of course. But when there are like equations, we parse them straight into LaTeX and we extract all that information. So we get the text and we get the LaTeX and we get the information from the tables all formatted in the Markdown. And it's all possible with a model that is a little bit bigger because that was the 3.5 from Microsoft. So it's 3 billion parameters still. Regular GPU, 16 gigabytes of VRAM should be enough to run it. And you get a processing engine that gives you a hell lot more information from the text than you usually would get with like regular OCR. And you can come up with those tasks. Yeah, we just decided, okay, let's do LaTeX. Okay, so we just created the data set and fine-tuned it. Yeah, so that's all. Those are VLMs. If you have any questions, yeah, I'm happy to answer.
Thank you, Piotr. Any questions from anyone? Please raise your hand.
There is one.
Okay, thanks for amazing talk. I have a question because you say that you can identify different images and so on without a specific training for things. So how this is really under the hood, because this language is really requires some training. I was discussing in the chat with a colleague how you can apply if you start to put fantasy images, for example, to analyze Game of Thrones or something similar.
I love those examples of fantasy images.
That kind of stuff. So
it tends to work less,
Thanks.
but I'm happy to answer. So, so how does it happen that you don't train and you still get that? It's because the model is actually trained not only on images. It's trained on text first, a lot on text, and then on images. So you get this pre-trained model that was trained on text. And from text, you get kind of like semantic relations between objects. Yeah. So, for example, a model learns that if you drink something, you can drink from a can, you can drink from a bottle, you can drink from the glass. And all of those objects exist in the same semantic meaning in the text. So it learns that, I don't know, the tail is connected to a dog, for example, and then from that pre-training on text, when you then apply the training on the images, it can reason those connections between the objects. So the fact that you can do zero shot is because it was first trained on text, and a lot of interactions between objects that are not present in object detection or like any computer vision data sets, because it would be just immense amount of work to explain those things through image. Through text is actually happening kind of on its own. So the knowledge is there. Fantasy images are are problematic. I always have at least one person on Twitter who, when I post about VLMs, they upload a screenshot from Final Fantasy and they say, you see, it doesn't work because whatever. So the problem, of course, is that data that is used for pre-training is, a lot of data sets that we have, and especially the largest data sets that we have, and especially those data sets that we can use because they are licensed correctly, are from real life. So the models understand, concepts about real world, but then when there is like a glow around the person that is not really happening in real life, it gets, a little bit misled. All of that can be solved with just fine-tuning on specific data sets. So there's that. That's how it happens. We have another question on the other side, I guess.
Come in.
Hey, really appreciate the talk. You're using Google. I was just curious what you're using to show it. And was this the Florence?
The tool is called CallUp.
Yeah.
And it's from Google. Everybody has that. If you have Google account, you can use it. You have a free GPU up to 8 hours, I guess. There are pro versions as well, but it's awesome to show something like that when you just hack things and you just want to change something and don't install everything and don't run it. So Google CallUp, that's the tool.
And is that using, you said the Florence?
The Google CallUp itself don't have the Florence, but I just skipped that part because I didn't want to bore you with the setup. But it works like any other Python environment because that's Python only. At least the Google Colab is. So I'm just installing, I'm just making sure that I have access to the GPU, and I'm just installing a few packages, all of them open source. And then I load few images, and I load the weights. I load the weights from Hugging Face. Not sure if you heard that, but yeah, are hosted on Hugging Face. So I'm just pulling that with Transformers package. That's it.
Thank you. That helps.
Any other questions? If not,
I have a question.
Okay.
I have a question. I was just waiting for someone in the audience, and if there are no, I'm just curious. How does the landscape look like when it comes to those models and processing video or even real-time video?
So how it looks? I can tell you that we are not yet there to process real-time. But I can tell you that a year ago, a single frame was processing for like 5 seconds, and today it processes at 400 milliseconds. So the progress, at least for now, within those like very short time window between 2021 and now, is like 10x every year. So we are, I believe, in this place where we are on the verge of starting to process real time. I showed you this example with like tracking basketball players and the ball. That can happen in real time. The only thing that will not happen in the real time is the part where you type in the prompt, and then you extract the first detection. But then the whole segmentation and tracking, you can process that in, I believe, like 30 frames a second or something like that. So it's not like 60 FPS or anything, but that can happen. And I get that question a lot because a lot of people who had experience with computer vision, they have this experience with like YOLO models that run in. I also don't believe it in those numbers, but they say it runs like 300 FPS or whatever. So yeah, we are not there yet because those models are significantly larger. So I was saying that the smaller model has 0.2 billion parameters, which is 200 million parameters. And YOLO Nano, for example, which is trashy model, but runs at 300 FPS, is, I believe, 3 million. So it's 200 million, 3 million. So you can see the difference in the size, and of course the size equals in compute time later on. Yeah.
Sure. Thank you, Piotr. Unless there are any other questions, let's thank Piotr again for amazing
Thank you very much.